So I've been talking a lot about the spring force and the force of gravity, and they have something in common, which we've seen, which is they both have a potential energy associated with them. They both, because they have this potential energy associated with them, and when they do work, it changes the potential energy of our system, and as a result, energy is conserved. So they have all these properties, and now we can finally put a label to those types of forces. We are going to call those types of forces, like gravity and like the spring force, we're going to call them conservative forces. So there's a couple different ways to define what a conservative force is. So one of the definitions is that the work done by a conservative force does not depend on the path the object follows. Let me try to explain that. So let's say you have a ball and you lift it straight up, and then after lifting it straight up, you bring it straight down, and then you bring it back to the position that you started in. If you want to know how much work gravity did during that whole time, first you could calculate how much work gravity did when you brought it upwards. On the way, when you're pushing that object up, gravity is doing negative work. And then when you bring it back down, gravity did positive work. And when you return to that initial position, the negative work that gravity did while you were bringing it up and the positive work that gravity did while you brought it back down cancels out to say that gravity did zero work. Then let's say you bring it a little bit lower. Now gravity has done positive work to bring it back down here. So going from the middle to the top to back to the middle and down a little bit, when we consider how much work did gravity do, all we really care about is where did you start and where did you end up. Because anything that happens in the middle gets canceled out. You could also move your object horizontally and gravity would be doing zero work while you do that. So when we talk about how much work does gravity do, the work done does not depend on the path the object follows. It just depends on where did you start and where did you end up. What was your y initial and what was your y final? The same is true for a spring. When you're calculating how much work a spring does, as an object, let's say, moves back and forth and back and forth and back and forth, anything the object moves to the right is going to get canceled from when the object is moving to the left. So all that really matters is where does your spring start and where does your spring end up. Those are the two things that matter when you're determining how much work the spring force did. So that's one way to define what a conservative force is. Another way, a similar thing that we're saying the same thing here, is to say that the work done by a conservative force only depends on the initial and final positions of the object. That's kind of what I was talking about, that it does not depend on the path. Another way to understand which forces are conservative forces is just to say any force which has a potential energy associated with it is a conservative force. So gravity has a potential energy associated with it, and the spring force has a potential energy associated with it. So both of these forces are conservative forces. But really, the best way to understand what is a conservative force is just in the word itself. Conservative forces conserve mechanical energy. Okay, so that means that when a conservative force does work, whether it's positive work or negative work, when a conservative force does work on a system, mechanical energy is still conserved. Okay, the mechanical energy does not change. That's going to be different when we look at non-conservative forces, because a non-conservative force will change the mechanical energy of our system. So this is really the best definition of what is a conservative force. A conservative force conserves mechanical energy. Okay. Let's look at some examples of non-conservative forces. Let's consider a marathon runner. Okay. And if that marathon runner ran a marathon that happened to be a circle, like you start and end the marathon in the same spot, the work that marathon runner did definitely depends on the path that he took. It does not just depend on where did you start and where did you finish. So this marathon runner would say path does matter when determining how much work he did. Something like the force of gravity, when determining how much work gravity does on an object, just where you start and where you end up is all that matter. For forces that are not conservative forces, the path that you take from where you start and end up does matter. Okay, so that's one way to understand what a non-conservative force is. The types of non-conservative forces we're going to be dealing with are pretty much anything except for gravity and the spring force. Really, the only conservative forces we're going to deal with this semester are gravity and the spring force. So everything else is a non-conservative force, especially any forces exerted by people, other forces like tension, normal force, thrust force, friction. These are all examples of non-conservative forces because the path that an object takes while that force is pushing on it matters when we calculate how much work that force did. And another way, and this is what I think is the best way to define what a non-conservative force is that when a non-conservative force, or when non-conservative forces, do work, the mechanical energy of the system changes. Okay, so we're going to go through a couple examples now where we're going to show how conservative forces do not change the mechanical energy of our system, but non-conservative forces do change the mechanical energy of our system. So let's look at this. Read through this, press pause, take some time to read through this because this can really help you understand what we're dealing with when we talk about non-conservative forces. This term here, W sub NC, this represents the work done by non-conservative forces, like your hand pushing on something or tension of a rope pulling on something. And I just want to know, based on how we're defining it here, I want you to think about which of these equations do you think is how we're going to incorporate the work done by non-conservative forces. So press pause, read through this, and press play when you're ready to go through it together. Okay, so I want to show that if a non-conservative force does positive work, we increase the total mechanical energy of our system. And if the non-conservative force does negative work, we decrease the total mechanical energy of our system. And that is going to be represented by this equation here. So let's say your non-conservative force does 5 joules of work. Well, what does that mean? It means that we start off with some initial amount of mechanical energy, represented as Ki plus Ui, and now your non-conservative force, whatever it is, maybe you push on something, that puts 5 joules of energy into the system. So later, there's going to be more mechanical energy. How much more? 5 joules more. Okay, so by putting that term on this side of the equation, it represents energy, if it's positive, that you put into the system, so that now Kf plus Uf is 5 joules bigger than Ki plus Ui is. Similarly, if your non-conservative force does negative work, it's taking mechanical energy out of the system. So now if this is like, let's say, your non-conservative forces do, let's say, negative 3 joules of work, now Kf plus Uf is going to be 3 joules smaller than Ki plus Ui. So that's representing taking work out of the system. Let's come back to our work energy theorem from last week and put this all together. So this is what we said last week. The net work done on our system determines how the kinetic energy changes. And remember, the way that we calculated net work was we looked at each of the forces that was acting on our system, and we figured out how much work each of those forces was doing, and then we added it all together. So this is just the work done by each force and then added together. So what I can do is I can separate the net work into how much work was done by conservative forces and how much work was done by non-conservative forces, right? Because the sum of these two should be the total work. And I can say the total work done by the total work done by conservative forces is equal to negative of the change in potential energy. And then this is still just the work done by non-conservative forces. And now if I rewrite delta U as U final minus U initial, and delta K as K final minus K initial, I get this expression over here. Okay, so it's coming from our work energy theorem, and I'm saying that my initial kinetic plus my initial potential, that's my total initial mechanical energy, plus any work done by non-conservative forces. So these are forces that are not included in the potential energy here. That's going to be equal to my final mechanical energy, which is K final plus U final. And we can say if the work done by non-conservative forces is positive, if this number here is positive, then that means the total mechanical energy of our system increases. If the work done by non-conservative forces is negative, then that means the total mechanical energy of our system decreases.